our example is going to be to find the curvature of what's called a helix. And this one is going to be given by r equal to sine t, cosine t, 2t. That's kind of that sketch of the path we're tracing out in kind of 3D. And so we're going to follow these steps I gave you right here. First, we're going to parameterize this r of t in terms of arc length. So that involves first finding arc length. So I know s of t is going to be the derivative from the very first time. So we'll go ahead and call that time 0, because we're not given any other information, up to some t. What we want to compute is just the derivative of r, its magnitude, and we're going to integrate that. And remember, we use that special notation here so I don't mix up my t's, but if it is comfortable for you to write r prime of t dt integrated from 0 to t, go ahead and do that. It's not going to bother me. So my r is sine t cosine t 2t. So just writing u's in, that's sine u, cosine u, tu. And I want to know the integral of the magnitude of that derivative. So derivative of sine gives me cosine u, derivative of cosine gives me minus sine u, and derivative of 2u just gives me 2. From 0 to t. So integrating from 0 to t using my magnitude formula is square root of all those components squared. So cosine squared u plus sine squared u plus 2 squared. Cosine squared plus sine squared is just 1. So that's integral from 0 to t of 1 plus 4 du. So that's integral from 0 to t square root 5 du. That's square root 5 times u, evaluated from u equals 0 to t. So that's just square root 5 times t minus 0. So square root 5 times t is going to be my curvature. And then what I wanted to do eventually was write r in terms of s. So if I know s is square root 5t, then that tells me that t is s over square root 5. And then I can go ahead and plug this into my r. My r of s is going to be where I take all my t's and replace them with something that depends on s. So it's sine s over root 5, cosine s over root 5, 2 times s over root 5. Now I've done that first step, parameterize r of t in terms of s. And then I just have to compute t, the derivative of that. So t is equal to r prime of s. So that's going to be derivative of this with respect to s is 1 over root 5 sine s over root 5. Derivative of cosine minus 1 over root 5 over sine s over root 5. Sorry, in the first one I forgot to change over to cosines. I hope when you all see me make these silly mistakes and then catch myself, you're like, oh, it's not so bad when I make those silly mistakes when I'm working on my web work. Derivative of 2s over root 5 is just 2 over root 5. And that's our t vector, the derivative of r with respect to s. Now I just want to know my curvature. How does that tangent change with respect to arc length? So unfortunately, we're going to have to move this over to a new page. My kappa is my magnitude of t prime of s. So that's going to be, sorry, I'm going to have to copy over my t again. 1 over root 5 cosine s over root 5, I think it was, minus 1 over root 5 sine s over root 5. Maybe that was just 2 over root 5. I'll go check real quick. 2 over root 5 minus plus sine cosine. We're good. Okay, so I'm going to have to take another derivative. Got stuff crammed in too much there, so I'm going to take my derivative. Now I'm going to get 1 over 5 out front. 1 over root 5 times 1 over root 5 is 1 over 5. Cosine becomes a sine s over root 5. And then that gives me a negative. Again, my root 5's combined to a 1 over 5. Sine changes to cosine. And this time, no sign change, so I keep my negative. And then derivative of a constant with respect to s is just 0. And finally, we're just applying that magnitude formula again. Good thing we practiced it so much in section 9. Negative 1 over 5 sine s over root 5 squared plus negative 1 over 5 cosine s over root 5 squared plus 0 squared. It's going to be square root 1 over 25 sine squared s over root 5 plus 1 over 25 cosine squared s over root 5 plus 0. Sine squared plus cosine squared is 1. This becomes square root 1 over 25 times 1. That's just 1 over 5 is my answer. So everywhere on this thing that follows sine, cosine, and xy, and then 2t and the z has the exact same curvature. And it kind of makes sense because you know cosine sine makes a perfect circle. So like how quickly you're spinning around probably doesn't change anywhere as you travel along that path. Now I made you do all this one time. I'm just going to tell you that there are other ways we can calculate curvature. So you can calculate curvature as the magnitude of t prime of t divided by the magnitude of r prime of t. So ignoring all this parameterization, solving for s, you can just use that formula. Or if you don't even want to compute t prime of t, you can compute it using r prime cross r double prime, the magnitude of that, divided by magnitude r prime cubed. Sorry, I want to be clear. These are the ones that depend on t. Cram all that in real quick. So this first time we practiced it this way because I really want you to understand what curvature is. And if you forgot one of these formulas on an exam, you could figure this out really straightforwardly just based on what you know of derivatives and arc length. But there are these other two formulas that you're welcome to use. R prime cross R double prime over R prime cubed, taking all those magnitudes, or T prime over R prime. I just wanted to fix that so you can see it well. So please write those equations in your notebook, and we'll practice one of them in a second.